Hi everyone, welcome to Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we're going to have a presentation by one of our students, Oscar, who did his project in ROS Basics in 5 days for Python. So he's going to show us a couple of nodes that he worked on for a Turtlebot 3. And he's going to show us here in our Real Robo Lab what the nodes do and explain to us the project. So hi, Oscar, how are you doing?
Hey, Olio, how are you doing? Thank you very much for this space.
Thank you for coming. So so whenever you want, you can start sharing your screen and show us what your project is.
Okay, so let's get started. Let's share the screen right now. Let's go.
Okay, I can see your screen.
You have visual. You can hear me well, I guess.
Yes, very well.
Okay. So if I understood, we are putting in two blocks. So first block, it's about the demonstration, and then explain the code, how I solved the main problems of this project, right?
Mm-hmm, exactly.
Okay, so let's get started. So this project is about a robot that is able to find a wall, the closest wall, and after finding this closest wall, is gonna be able to follow on its right side to complete one lap. So let's have fingers crossed and launch our program. So here we go. Okay, what is this?
Line 11, column 9, you must be missing some sort of symbol or something in that main dot launch.
Okay.
So if you open up there it is. So main.
Yeah, it was.
Yeah, there it is.
Times a lot of today. Okay. Okay, let's go now. So in this part, as you can notice, the robot will start first looking for a wall. So we have some feedback on the terminal of this visual. I will highlight the main window so we can have a bigger picture. Normally at this point, the robot found a wall and will start moving forward towards this wall.
Now it's lining up along the wall, I guess.
Exactly. Now it's we have some delay on the video, but yeah, normally you can see it aligned with the wall and starts following the wall, and at the same time providing some feedback about the moved distance at the current time.
I see. So at this point, if I understand correctly, you divided this into a service, a main node, and an action server. And the server is doing the finding the wall, right? Or is the service still running right now?
Yeah, the service, actually the service server, it's the one that was in charge of finding the wall and aligning to it.
Okay.
And now what we're seeing right now, it's the behavior of the wall following.
Mm-hmm.
And also we are applying the concept of asynchronous capabilities of action server in order to, in parallel, while the robot is moving, retrieve the odometry and being able to compute the current distance until now.
Right.
So far so good. The robot's still moving.
It's like halfway there, yeah.
Real life not betraying the simulation until now.
Oh, this is the first time you try it in the real robot?
No. But as you know, you never know when.
Yeah, you do not. And I can see that there's some issues in the feed for the camera. So, but it's working. But that's work for me to figure out why that's happening. All right, so it's almost done.
Yeah, we're about to complete one lap as expected.
And then
Like
the
if we
robot,
were,
will it stop or will it keep going?
so yeah, so this was the interesting part of the actions that even if not specified in the project description itself, I applied this status functionality. So when we more or less completed one lap, that means when the robot moved around 6 meters by now, the status will indicate that the action is done. So
Oh,
at
I
this
see.
point, the robot will stop. So we're close to 6 meters, a bit more. I added a security march in that case. And right now, in a few centimeters, the robot should stop.
Oh, there it is.
And yeah, as we can see in the terminal, we get some signal of the odometry that was stored each second. And we were watching in parallel the continuous feedback about the current
Awesome.
move
So
distance.
it moves, a whole lap is around 6 meters, and great.
Yeah.
All right. Well, it works perfectly. So if you don't mind, go ahead and show us how you did each one of these sections.
Yeah, that will be my pleasure. So for that end, I guess I will stop this first. Now let's move to the code part. So as you could see, the presented demonstration covered the basics of the expected behaviors in this project. That means a wall following behavior, which relates to the one of our nodes, finding a wall behavior and providing odometry as well as the move distance. The project was structured in 3 main nodes. That is the server node, the action node, and the client node. Let's take a look at the client node right now. The client node, it's the spot in the code from where we launch everything. Particularly, I created a class called Turtlebot 3, which is the entry point for all functionalities. So let's take a look at this class right now. I would like to highlight your attention in principal elements. That is the constructor of this class, in where we declare all necessary tools, that is publisher and subscriber to the necessary topics, as well as other variables. And particularly in this constructor part, I set up the service server client and the action server client with the corresponding lines to this end. So now let's find out how I approach the question how to follow a wall on the right side of the robot. For that, I apologize for this scrolling dot, but we will get to the functionality. So here we are. I created this function in the class called follow real wall. The essential part of this function relies on 3 conditions. 3 conditions. The first one of them evaluates the frontal distance. So the goal of this is to avoid a frontal obstacle. So whenever the front ray measured distance is under 0.5 meters, first of all, I reduce a bit the linear speed. So we keep a bit of stability. And I input an angular speed of omega 5. Omega 5 tuned experimentally, in this case, takes a value of 0.3 radians per second. In the case, we don't have any frontal obstacle, but still we are turning to the left, so we may find still a wall on the right side, and the distance may occur to be under 0.2 meters. In that case, we applied still a rotation to the left, but for a different value, a slower value of omega 2. Omega 2 in this case, around 0.12 radians per second. Finally, when the robot, because of this adventure in this turning place will get away from the wall, getting off enough to be at a distance on its right side bigger than 0.3 meters. We try to get it close with an omega-3 angular speed, negative in this case.
So it goes back towards the wall.
Exactly. Mm-hmm. We're going back towards the wall. In this case, it happens that half of omega-2 speed, it shows appropriate behavior to not get too close to the wall again and increase the zigzag effect that this behavior may create. So if none of these conditions is true, we just cancel the rotational speed and we recover nominal linear speed. So just to keep going forward. This covers the part one of the project. Now, I hope you're following me, all of you guys.
Yes,
and now I would like to take you to the part two of the project. The part two of the project, I will first explain you the strategy, and then I will explain you how it's connected with the service server.
Okay.
So we will stay for the moment in the Turtlebot 3 class. We will move to the function that it's called find real wall. And here we are. We are in the function find real wall. The main elements of this function, first of all, we assume that the robot is oriented on a free obstacle position. That's what you just saw on the demonstration at the very beginning. Then, since we have other obstacles around and based on the constraints on the project, we can decide to focus only on the front half laser rays of the robot. In such scenario, we will be at each iteration in this while loop, we will be constantly looking for the shortest measure of distance until this shortest measure of distance will fall into the front area of the robot. In this case, we retrieve the index of the corresponding smallest distance, and these indexes that you are looking at account for more or less an angle of view of 5 degrees on the front area of the robot. Using this strategy will kind of ensure that we don't miss the front area of the robot. Otherwise, because the robot is turning and we have some different frequencies about the topics and the node itself, I think this can, at least this worked for this purpose. So until this part of the code, the robot found a wall. Now, in this part of the code, we input a linear speed to make it move forward and stop at a distance of more or less 0.3 meters. Then we stop again, and we apply a similar strategy in order to align the robot to the right wall. In this case, we are not picking the front half, but the right half of the laser rays. Similar strategy, we constantly look for the smallest distance, and once the smallest distance corresponding index falls into these values, which again corresponds to an angle of view of more or less 5 degrees on the right side of the robot, when this condition is true, then the robot stops and starts moving to follow the wall. So this is accounts for the strategy. Now, if we go to the service server code, here we find the classic, let's say, infrastructure code of the service server. And in the callback function, we just declare a Turtlebot 3 class object, and we make a call, in the case, a call to the function to find a real wall. So until now, we covered part 1, we covered part 2. Now let's tackle the part 3 corresponding to the action server. And now we get out from the Turtlebot 3 class to go to the record odometry action server file. Here again, following the infrastructure of a service server, we have a class that I named record odom class. In the constructor of this class, I declared the action server, the subscriber, and some helpful variable to transfer data from the topic to my code. And after this part, we can go to the interesting part of the action server, which stays in the goal callback function. Some points were requested in the project, like the fact of iterate at frequency of 1 hertz, so take odometry reading each second, and the fact of using a 0.32 data type to store the odometries. So let's jump directly to the odometry part, which is here in this while loop. So the odom topic provides us with position and orientation information, which can be useful to split them in different variables. For the position information, it's already in Cartesian coordinates, so it's already ready to be used. On the other hand, if we want to build this odometry vector composed of x, y, and theta angle, we need to transform the orientation information, which is in quaternion representation, to Euler representation. And this can be done thanks to the function Euler from quaternion, which provide us, among other stuff, roll, pitch, and yaw angles. But here we just care about the yaw angle. So that way, with the position and the yaw angle, we can now build our odometry vector, as we can see here. And in order to create a list of odometries as requested on the odom record action message, the list of odoms will be the final result of the action once it's accomplished. We take the result variable and we access to the list to start in a structured way this data. So this is for the part odometry storage, and for the last part of this action part, it's about computing the moved distance from the robot. And what we can do here is to each iteration store the current odometry in an auxiliary variable that I called old odom, and basically use the position from the current position and old position to compute a delta applying the Euclidean distance formula. And all the deltas are stored in a current total variable as expected in the feedback
And
message.
that's what we were seeing in the terminal, correct?
Exactly. We were, I considered pertinent to see the feedback on the terminal. And that's kind of the main idea of this action strategy. And of course, when the action is finished, that's a good question. When the action is finished, well, when the distance reached, when the move distance reached more or less 6 meters, it was experimental tuning again, the action will end and will provide a success feedback to the client. And so this covers the part of the action and how the client behaves when he receives its done. So let's go back to the Turtlebot 3 class, particularly in the wall following behavior. So this is the function we just saw together at the beginning. And here, the additional information right now is just the condition of the while loop. So the robot will move following the wall as far as the action is not completed. So when the action is done, the robot stops moving, and we will visualize, as you saw in the terminal, eventually the result. That means the list of odometries as expected. In resume, we have a client which has a Turtlebot class, and from this Turtlebot class, we can call the service to position the robot before start following the wall. And prior to following the wall, we start saving the odometries and computing the distance to get the final result.
Oh, so the odometry recording starts when the service starts.
Just before the action. I mean, sorry. Well, the service, if I understood well, just concerns the position in the robot.
Yes, yes, but what I'm saying is, does it
Yeah.
start recording the odometry when the service is being executed?
After the service.
After the service, okay.
Yeah.
Okay, okay.
Yeah. Anyway, the service, it's a synchronous call, so it's gonna block the rest. So yeah.
Great. This is the whole thing, right?
I'm done. That's
Great.
what I wanted to share with you.
Great. So, do you mind stopping sharing your screen so we can look at each other here?
Yes. So
All right. So I can see our. So congratulations, Oscar. It's a really nice project. Really well done. I really liked how you implemented the Turtlebot class, and that consequently makes everything else a lot simpler because you're instantiating. Yeah, you're managing it a lot really nice. So that's really nicely done. And let me ask you some questions that I was writing down when I was listening to you. So, first of all, I saw that you have a find real versus a find sim. So I'm assuming there were changes between the simulation and the real robot. Can you explain us what these are or why you had to do two functions?
Well, maybe I could come up with a simpler strategy. The only difference is speed values.
Oh, the speed values. All right.
Yeah. In practice, simulation values were higher than real robot.
Because you don't want you don't mind crashing the simulation, huh?
Yeah, kind of. So yeah, that's basically the main difference. But the algorithm is the same.
Okay, I get it. And a couple of things that I noticed too. So you talked about when you are trying to find the wall, you discard the back of the robot, right? Because I'm assuming there might be an obstacle in the back, and it might recognize it as the wall and turn that way, right?
Yeah.
So that's why you halved it. Okay, so I know this isn't included in the project. So how would you manage this so you don't have to figure out a starting position and so that it goes to, like, do you have any ideas on how you could implement it so you take all the scan into account and recognize between, say, a wall and an obstacle?
Yeah, of course. Let's say that the starting position of the robot, it's a very specific starting position. So in order to make the rest of the algorithms, the functionalities to work. And of course, this is not real life. This is just a specific case. But I guess in this case, we should find different strategies to distinguish walls from obstacles. Exactly. I cannot give you an example because it's a bit out of my scope of background, but I know that you have strategies to find a trajectory, to create a map of the environment.
Yeah. Okay. Yeah. That's a little more into the navigation, but so I'm thinking of like so all you got information in this point is the laser scan, right? So an idea that I've seen it implemented before is to look at the distance of a consecutive amount of the scan value. So you know that they should be, if it's a wall, it should be long, and the distance values shouldn't vary that much. So let's say you take in a quarter of the scan value in a vector, and if the distance in that vector doesn't fluctuate too much, then you can assume it's a wall. And if it's on the same, like let's say in the back, there's a ton of obstacles that are very close, but you see the difference in distance, then you can say like, oh, that's not a wall. So that's just an idea. But yeah, you're right well, in real life, it could be like in a controlled environment where you do this from a starting position every time. So it could be like a real life thing, but I'm just talking about to like increase autonomy of the robot.
Yeah, right.
And okay, let me ask you one more question. Oh, another thing that I really liked was that the fact that you used the scanner, the laser scan, also to line up against the wall, because you could have just done a hard-coded value, like to figure out how much you have to turn 90 degrees, and you used the laser scan. So I really like that. So that's really nice, and that goes along the lines of increased autonomy. So that's nice.
Yeah.
And could you tell us, just last thing, some of the benefits of structuring your class like this, your Turtlebot class, and why, if there's a reason? I noticed that you also have the recorded odometry class. Is there a reason why you didn't put it into the Turtlebot class, or did it not? So those two things.
Well, actually, that's a point in which I was thinking. Well, first of all, the fact of isolating the behavior of the robot from the infrastructure code. What I call the infrastructure code, it's the client, the service server, and the action server. So it really makes it easier to make modifications, because mentally you are focused on the intelligence of the robot, and then you just call a function to activate it. So from that point of view, it was easier to manage and maintain my code. Then, yeah, in the way action server is implemented, it uses a class. At the present time, in one moment, I try to concentrate on that to really make it all in one single class. So for reasons of time, I decided to stay like that. But I think that can be a way of improvement or not. It's just a matter of to try it and to see if it really has some pertinence or not.
Right. Okay, yeah. So I always encourage students to do exactly what you did, because as the project grows, and it just becomes a pain if you don't use classes and if you don't organize it carefully. So in the main program, you can just call a function, like you said. All right. Well, I think that's it for me. So again, congratulations. It was a really nice project, really well done. And yeah, and I mean, everyone, to everyone else that's watching, please, if you're in the construct and you're doing the course, please, I encourage you to do what Oscar did here, so you can complete your learning in the course, which is why we do this, to make sure that we give our students something that they can take away from and provide real learning. And this is like the last step of the learning. So I encourage you guys to do the same. And Oscar, really well done. Thank you very much for your time. And we hope to see you again soon for another course if you're interested, or just to see you around for more ROS learning.
I think you will watch me for the C++ part, hopefully.
Okay, well, we'll be here, and we'll check it out when you have it.
Thank you. Great.
All right, guys. So that's it from us. So make sure you subscribe and watch our videos here at the Becoming a ROS Developer, and we'll see you next time for our next presentation, you guys. Bye-bye.
Bye.
Okay, perfecto.